Thank you very much. I will present you our work dealing with smart functions for carbon nanotube bolometers. First, I'm coming from France in Europe, in Normandy. Maybe some of you know the Mont Saint-Michel here. This would be the outline of the talk. Just a few words about bolometers, resistive bolometers. This has been introduced in the first talk, so I will try not to spend too much time on it. And after, I will show you what is smart with the bolometers we are using. So the context of infrared imaging system. So a growing context with a main application for process monitoring, pedestrian detection, and thermal building diagnostic. And for the infrared imaging system, the uncooled resistive bolometer represents more than 95% of the market. So this is to illustrate the situation. And resistive bolometer principle can be summarized with this schematic, with a thermal mass here connected to the substrate through a thermal conductance. And the incoming optical power is absorbed on the top layer and will eat up the thermal mass. And if we implement a thermistor resistance which varies with temperature, we are able to monitor the incoming optical power. So the incoming optical power is transformed into thermal power because of the absorbing layer. And the thermal power will consequently produce some temperature variation that is sensed through a resistance. And if we bias the resistance, for example, with the current, we will measure some voltage that will vary with the incoming power. So these are the metrics for the bolometers with the sensitivity. That will be better if the thermal link is low conductance. And with the time constant, that would be higher with a low thermal conductance and a high thermal capacitance. That was discussed in the first presentation. So this is the device we are using. So it is a silicon thermal mask with a silicon thermal link. And what is interesting is the absorber using vertically aligned carbon nanotubes to get what is called the darkest matter in the world with the absorption coefficient close to 100%. So these are the device used. So you can see here really dark matter here. The size is quite big, so the device is slow, but it's a device to implement the smart function you will see afterwards. So here it's a 3 millimeter wide disk. So what is smart? If we refer to the IEEE definition, what is smart for a sensor is functions that are beyond those necessary for generating a correct representation of the sense or control quantity. So smart is combining the pre-processing with the sensor, so filtering and amplification, and maybe also some analog to digital conversion, also communication protocols. So this is one aspect of smartness. The other one can be given by this. These are control and diagnostic functionalities, such as configurability, adaptability to the environment, measurement range selection, compensation, self-test, that are implemented in some kind of sensors we have. For example, the accelerometers with self-test features and measurement range selection. So this is what we want to do, is to have some kind of a heat balance bolometers, to have smart functions for bolometers. We can tune the measurement range. We can have self-test or self-identification functions. So this is our work here. So to do this, we are using the electrical substitution principle that says that whatever the physical nature of power is, the thermal equilibrium is the same. That means that either the incoming power is optical or electrical, we can balance the power to keep the same temperature. So we will use the joule power, so electrical power, to compensate for optical power, and using the bolometer in closed loop mode. So here is a bolometer with conventional conditioning electronics, amplification and filtering, and what we had is a feedback path to equilibrate the temperature. So, and the feedback power will compensate for the incoming optical power. Doing this, we can take benefit of the advantage of the closed loop mode that are reduction time constant. To get a wider bandwidth, we can choose the operating point. We have a direct power reading, but since we can stimulate the bolometer, we can also implement smart functions such as a self-test or self-identification or measurement range selection. I will only show you some slides with the self-identification and for the to illustrate the reduced time function in the next slide. So here, this is the schematic for the closed loop mode, and what I will show you are experimental results showing the bandwidth improvement going from open loop to closed loop mode operation. So this is the open loop. In open loop, the input is the optical power here, coming onto the bolometer with the conditioning electronics, and the output will be some voltage representing the temperature of the bolometer. So here we are exciting the bolometer with square wave optical power. So this is in open loop. We have temperature variation. So heating up, cooling down, heating up, cooling down, typical of the first order thermal system. And if we go in closed loop mode, then we have the feedback and the output is here. And we can see that temperature is kept constant because of closed loop mode operation. And the time constant is reduced, the bandwidth is increased, and we can see the shape of a square wave in the feedback. So this is just to show you the closed loop mode operation. And now I will go on with the self-identification function. So it's a diagnostic function that enables to know how is the sensor working, and it could be useful to monitor the evolution of the system during time. So aging of a system to extract its thermal parameters. So we are using this scheme. The bolometer is put into a vacuum chamber. We have the a laser beam to income power on the bolometer, and we are in that vacuum chamber in order to change the pressure and to change the thermal exchange between the bolometer and the environment. So we will be able to change one parameter, that is the thermal conductance of the bolometer compared to the environment, and we will try to extract this parameter. So as the pressure increases, the thermal conductance would increase, and then the responsivity should decrease, and the thermal constant should decrease. So we are implementing least mean square adaptive algorithm into the microcontroller to extract in real time the estimated parameters. So for this, we are comparing the output here, measured output, and the input we stimulate to the bolometer. So we are stimulating the sensor. The stimulation is a pseudo-random sequence to excitate various frequency modes to have a better extraction. So here on the top, you have the input. This is the measured output. And during the experiment, after 2,000 seconds, we shut off the pump, and the pressure goes up to atmospheric pressure. So what we can see on the output is that at low pressure, we have a high amplitude and quite low system. This is what we expected. And at room temperature, atmospheric pressure, we have less amplitude here, but faster system. This is what we expect from theory, because of thermal conductance is rising up. So then the responsivity will reduce, amplitude reduce, and the time constant will reduce. So we have a faster system. And this is the real-time extracted parameters. Let's show the extraction of the estimated gain and estimated time constant that will follow the variation of the output. So extracted from this and this thanks to the algorithm. So this is the self-identification. That means that we self-stimulate the bolometer to extract its thermal parameter. Our actual work on the self-identification in closed loop mode. So these are some first results. So in closed loop mode, then the temperature will be kept constant, and we will be able to work at a faster speed. but still we can extract the parameters here. So same kind of experiment going from low pressure to atmospheric pressure. And we are working on the uncertainty of the extracted parameters to be able to have that kind of graph to monitor really precisely the aging of the system and extraction of the thermal parameters. So I've shown you some feedback operation of resistive bolometers with resistive bolometers with a carbon nanotube absorber for the high absorption, 90.99%, and some smart functionalities with the example of the self-identification function to make more than a sensor, in a sense, a smart sensor. And I thank you for your attention, and I will be pleased to answer questions if you have.